In this problem, we have a Venturi meter, and how a Venturi meter works is it measures the flow rate by constricting the pipe and then measuring the pressure drop from across that constriction. And so here it's a little different than what we're used to seeing in that the flow is going vertically upward. But you see at position A, we're at 12 inches, and then we have this constriction down to 6 inches. And then what we do is we put a pressure gauge and we measure the pressure drop between points A and B. And then from that, we are able to calculate what the volumetric flow rate is going to be. And so the little complication of this is that we are using very old school technology of a manometer to measure the pressure drop. And so we are told that the deflection of the mercury is 14.3 inches. And so the this dark fluid here is representing the mercury. So that's a deflection of 14.3 meters. Determine the flow of water through the meter, assuming that there are no head losses between A and B. And so we're assuming that there, and we'll talk about this later, that frictional losses between point A and B are negligible. And so once we know the pressure drop, we should be able to apply Bernoulli's equation and calculate the volumetric flow rate. So what I've done here is assembled some information. We need the density of mercury, which we can look up as 844.9 pounds per cubic feet. Density of water. The specific gravity of mercury is just the ratio of the density of mercury to water, and so that's about 13.5. And then I have some elevation information that we're going to use, and so we're going to use position A as our datum, as our baseline, so we're going to set that at 0. Position B, since we're flowing up, we're going to take our elevation change into account. That is going to be 30 inches or 2.5 feet. Then we have the diameters of 12 and 6, and then from that we can calculate the areas. Now the first thing that I like to do is just go over, let's forget about the manometer for now, and let's just assume that we were able to, we just put a pressure gauge in, a simple that's easy to read, and it just gives us a number. So what we're going to do is we're going to apply Bernoulli's equation to this system to solve it. And the Bernoulli's equation for this system is going to be the standard form of this equation, where the pressure at A over rho g plus V squared over 2g plus the elevation. So this is the energy at A minus the head losses is equal to the energy at B. And so that's going to be the pressure, the velocity, and the elevation. Now, we are told that there are no head losses, so we can neglect that, and that is where we'll leave that for now. Now, what we need to do, though, we need to figure out what these pressure terms are, the PA and the PB, or the delta P. And so we need to look at the manometer figures and use our thinking of how this is going to work in the manometer. And so with the manometer, the pressure at L, so here is the pressure at L, is going to equal the pressure at R. All right? And so what we can do then is we can calculate, we need the pressure at A, right? We need the pressure A, we need the pressure at B. So what we can do is we can go step through here with our Bernoulli equation and solve for the pressure drop. And so here we've got PA over, and this is water, this fluid is water. So PA over rho g plus Z, so this height is Z, and then this height is 14.3 inches. So this total height between point A and L is Z plus 14.3 inches. That is going to equal the pressure at B over rho g, and that rho is for water, plus 30 inches, plus Z, and then we have the 14.3 inches. This is mercury. This is mercury here. And so that's going to be multiplied by the specific gravity of mercury. And so what we can do now is we can solve for the delta P, right? The delta P is what? PB minus PA, or if we want to keep it positive, PA minus PB. And so our Z is going to cancel out, all right? And our 14.3 inches is going to be subtracted, 30 inches is going to be subtracted by 14.3 inches. We do the algebra, we plug in for the specific gravity, and we get our delta P, right? Our delta P is going to equal 7.56 psi, right? If we want to put that in terms of head units, which is length, right, we divide by rho water times G, and that will be 17.436 feet. All right, but anyway, what we needed to know this pressure drop from position A to B, and a little bit more complicated than reading off of a pressure gauge. The other thing that we can use is that for incompressible flow, we know that the density at A is equal to the density at B. So I've already canceled that term out of our continuity equation. But we also are left with VA times the cross-sectional area at A is equal to VB times the cross-sectional area at B. When we are working with the Bernoulli equation, all right, we are going to what? We are going to need to know the volumetric flow rate. And so if you think about it, if we know the if we know the linear velocity, right? Remember, this is a volumetric flow rate at A, this is a volumetric flow rate at B. Because of continuity, the volumetric flow rates are the same at both parts. If we know the linear velocity, we know the volumetric flow rate because we know what the areas are. We know that VA and VB are going to be different because, of course, AB and AA are different. When we are working with the Bernoulli equation, what we would like to do is we would like to express the velocity in terms of one of those, in terms of the other velocity. So we eliminate one of the unknowns. And so that's what I've done here. Because now I know my pressure drop, I want to solve for the velocity. And it doesn't matter which one I choose as long as I choose one of them. Because if you look here, I know the heights, I know the elevations, I know the pressure drop now, I know the density, and of course the head loss cancels out. So what I do is I take VA and I express it in terms of VB, and then what I can do is I can go and simplify this Bernoulli equation. And so that's what I've done here. I've taken the delta P, the PA minus PB, and then I have here, so here's my delta P, so it's PA over PB. Notice that I kept it positive here. So this is the pressure is greater at A than it is at B. All right, and so now I have VA, that's just this term, so that is squared over 2G plus ZA, and then minus VB squared. So I move that over, VB squared over 2G, I move that over, and I move the ZB over. And so I've done this simply so that it's easier for me to solve. You see, now I have a quadratic formula, quadratic equation in terms of VB, and note that ZA, this is my datum line, this is equal to 0. ZB is 30 inches or 2.5 feet. And so instead of trying to solve this with a quadratic formula, trying to factor this and solve this by hand, I'm going to use a MathCAD solver. And so what that does is I input this into symbolic notation. I set a guess of V sub B, and so I just plugged in a guess of 10 feet per second squared, or sorry, 10 feet per second. And then I use the root function of MathCAD, and the notation of this you can look up, but it's simply what you do is you rearrange the equation into the f of x is equal to 0, and then you use this root function. After guessing, you use the root function and tell it to solve for v sub b. And when I do that, I get v sub b is equal to 32.018 feet per second. I can then solve for the velocity at A if I would like to. That is 2.44 meters per second, or I could put that into feet per second as well. Let's put that into feet per second. So that is 8 feet per second. And then I can solve for the volumetric flow rate. The volumetric flow rate is VB times AB. So that is 6.287 cubic feet per second. And note that if I had used V sub A times A sub A, that will give me the same answer. If I convert that to cubic feet per second, I get the same. So this is an incompressible fluid, and so the mass flow rate, volumetric flow rate, densities are constant from point A to point B. But this illustrates how a Venturi meter works. Where we have a flow constriction, we measure the pressure drop over that flow constriction, and by using some assumptions, we can easily calculate the linear velocity, and then from that calculate the volumetric flow rate. Now, one of the things that you could do, notice that we assume that there were no frictional losses. And later on, you will find that you can calculate what the frictional losses are going to be here. It'll be a little bit more difficult because if we don't know what the linear velocity is, it'll be an iterative calculation, but that is certainly doable.